Welcome! Today we are going to pull back the curtain on the invisible world that's all around us. We're talking about the fundamental pushes and pulls, yep, forces, that decide how everything moves, from a planet whipping around the sun to, the phone you might be holding right now. Okay, let's just dive right in. Seriously, just think about it for a second. As you're sitting there, the massive force of gravity is pulling you towards the center of the Earth. So why aren't you falling through the floor? Well, it's because your chair or the floor is pushing back up with a force that's just as strong. It's these unseen battles, these invisible interactions that we're going to make visible today. So here's our game plan. We're going to start with the absolute basics, what a force even is. Then we'll get into forces that need to physically touch something, and after that, the really weird ones that act across empty space. From there, we'll learn a super useful trick for drawing these forces, and finally, we'll see how to add them all up to figure out what happens next. All right, first things first, let's tackle that big question. What is a force, really? Well, at its core, the whole idea is actually beautifully simple, and it is the key to, well, pretty much all interactions in the entire universe. Yup, that's literally it. A force is just a push or a pull. That's the definition. Every single time something speeds up, slows down, changes which way it's going, or even gets squished, you can bet a force is behind it. And physicists measure all these pushes and pulls in a unit called the Newton, named after Sir Isaac Newton, of course. Now, here's where it gets really interesting. It turns out that every single force we know of can be sorted into two big families. You've got your contact forces, where things have to actually be touching, and then you've got your non-contact forces, which can somehow work their magic from a distance. Let's break those down. Okay, first up are the forces we know best, the ones we feel every single day. These are the forces that require physical contact, the pushes and pulls that you can literally feel on your skin. So this one sounds a little technical, but I promise it's not. It's that force we talked about a minute ago. In physics, the word normal just means perpendicular, at a perfect 90-degree angle to a surface. It's the upward push from that surface that stops everything from just falling right through it. So think about it like this. If you put a box on a table, gravity is pulling that box down, but the table pushes back up with an equal and opposite normal contact force. The two forces are perfectly balanced, and so the box just sits there. It's simple, it's elegant, and it's happening literally everywhere you look. Next up is tension. Anytime you pull on a rope or stretch a rubber band or hang a picture from a wire, you are creating tension. It's that pulling force that gets transmitted all the way through a string or a cable when it's being pulled tight from both ends. And of course, we've got to talk about the forces that always seem to be trying to slow things down. Friction and air resistance. Friction is that force that kicks in when two surfaces are trying to slide past each other, like a box grinding its way down a ramp. And air resistance? Well, it's really just a special kind of friction that happens when something moves through the air, like the force that pushes up on a skydiver and stops them from falling faster and faster forever. Okay, let's switch gears and talk about the other family of forces. And this is where things start to feel a little bit like magic. These are the non-contact forces, the ones that can push or pull on something without ever physically touching it. They do this by creating something called a field. In our universe, we deal with three main types. You've got the magnetic force, that's what makes a compass point north and what sticks a magnet to your fridge. Then there's the electrostatic force, which is the same reason a balloon sticks to your hair after you rub it. And finally, you've got the big one, gravity. It's the force that keeps planets in orbit, and, unlike the other two, it only pulls things together. It never pushes them apart. So we know what forces are, but when you have a bunch of them acting all at once, things can get messy pretty fast. So how do physicists handle that? How do they simplify it all? Well, they draw a picture. And this little picture is one of the most powerful tools in all of physics. It's called a free body diagram. The whole idea is to take the object you care about, the body, and just represent it as a simple dot or box. Then you draw arrows pointing out from the center to show every single force that's acting on it. It's a way to make all those invisible forces totally visible. And making one is just a simple three-step process. First, you draw your object as a dot. That's it. Second, you figure out all the forces pushing or pulling on it. Gravity, friction, tension, all of them. And third, you just draw and label an arrow for each one. And boom, you've just created a perfect map of the physics of that situation. And check this out. This shows you just how powerful this technique is. On the left, you've got a pretty complex scene, right? A speedboat cutting through the water. But on the right, you have the free body diagram. The boat is just a dot. And now we can clearly see the four main forces in this tug of war. It's weight pulling it down, the water's upthrust pushing it up, the engine's thrust shoving it forward, and all that resistance from the water and air trying to drag it back. It becomes instantly clear.
All right, so now that we can actually see all the forces at play, we can take the final crucial step, figuring out what their combined overall effect is. What happens when you add up all these different pushes and pulls?
Well, this big overall force, it has a name. We call it the resultant force. It's the grand total you get when you sum up all the individual forces, making sure to pay attention to their directions. And the resultant force is the thing that tells you if an object is going to speed up, slow down, or just stay put. Take a look at this falling object, for example. Its weight is pulling it down with 50 newtons of force. But at the same time, air resistance is pushing up with 20 newtons. See, the forces are unbalanced. To get the final score, the resultant force, you just subtract the smaller one from the bigger one. So 50 newtons down minus 20 newtons up, that gives us a resultant force of 30 newtons, still pointing down. And that's what makes the object accelerate towards the ground. But what happens if the forces are balanced? Let's go back to our trusty box on the table. If its weight is 50 newtons pulling down and the table's normal force is 50 newtons pushing up, well, they cancel each other out perfectly. The resultant force is zero, a big fat zero. And when that happens, there is absolutely no change in motion. The box just stays right where it is. Okay, so adding and subtracting forces is pretty straightforward when they're all in a nice straight line. But what happens when a force is pulling at an angle? Let's try a little puzzle. Imagine a kid is pulling a little toy trailer, but they're pulling the handle up at an angle. Is all of that effort, all of that pulling force actually helping to move the trailer forward? The answer is nope. And to understand why, we can do something really clever. We can break that one angled force down into two separate parts. You see, part of the kid's pull is acting horizontally. That's the part that actually moves the trailer forward. But another part of that exact same pull is acting vertically, which just slightly lifts the trailer off the ground. So only the forward-acting bit is doing the useful work here. And this is the most important part to remember. Those two separate parts, the horizontal and the vertical, when you put them together, they have the exact same effect as that original single-angled force. We haven't changed the physics of the situation at all. We've just looked at it from a smarter perspective. This is a powerful trick physicists use all the time to solve really tricky problems. So we've gone all the way from simple pushes and pulls to drawing out these complex interactions. We've literally made the invisible visible. So I'm going to leave you with this question. Just look around you right now. Look at the chair you're in, the light coming from your screen, the very air that you're breathing. Now that you know what to look for, what forces are shaping your world right this second?